Hi everyone, I'm Sam. Today we are going to talk about superconductivity. Superconductivity is when certain materials can carry electricity without losing any energy, but only when they are cooled to extremely low temperatures. Imagine if electricity could flow through a wire endlessly without any resistance. That's what superconductivity is all about. To help you understand, think about how electricity from a power plant reaches your home. Usually, some of the electricity is lost along the way due to resistance in the wires, so you might only receive about 94% of it. But if we used superconductors, you would get all 100% of the electricity. Nothing would be wasted. This isn't just a neat idea. It has real-world applications. Superconductors can make power transmission much more efficient, saving energy and reducing waste. They also allow us to create extremely strong magnets, which are essential for devices like MRI scanners in hospitals that help doctors see inside the human body. But how did we discover superconductivity? To answer that, we need to go back in time and explore the history of low-temperature research, because superconductivity only happens at very low temperatures. The early history of superconductivity is closely linked to how scientists learned to cool things down to such low temperatures. Our story begins in the early 1800s with a young British boy named Michael Faraday. Michael worked as an apprentice in a bookstore. Whenever he had free time, he loved to read science books, especially about chemistry and physics. He was fascinated by how the world worked. In London, there was a famous scientist named Sir Humphrey Davy. Michael saved up and attended one of Davy's lectures at the Royal Institution. He took very detailed notes during the lecture, and using his skills from the bookstore, he bound his notes into a neat book. With courage, he presented this book to Davy, hoping to work with him. Impressed by Michael's dedication and enthusiasm, Davy hired him as his scientific assistant. At the Royal Institution, Michael helped Davy with many experiments and learned a great deal. One area that intrigued Michael was how to turn gases into liquids. At that time, scientists didn't fully understand how gases behaved under different conditions. In 1823, Michael conducted an experiment where he placed chlorine gas into a sealed glass tube. He increased the pressure by compressing the gas and cooled the tube using a freezing mixture. To his delight, the chlorine gas turned into a yellow-green liquid. This was the first time anyone had successfully turned a gas into a liquid using both pressure and low temperature. This discovery was important because it showed that gases could be changed into liquids, opening up new possibilities for refrigeration and cooling technologies. Encouraged by his success, Michael continued experimenting with other gases. He improved his methods by using strong glass tubes that could withstand high pressure. By heating or cooling these gases and observing how they reacted under pressure, he was able to turn gases like ammonia and carbon dioxide into liquids. This was a significant achievement because these gases were previously thought to be impossible to liquefy. Michael's work showed that gases weren't always destined to stay as gases. Under the right conditions, they could become liquids. This changed how scientists thought about gases and helped them understand how to manipulate their properties by compressing and cooling them. However, some gases like hydrogen, nitrogen, and oxygen were stubborn. No matter how much pressure Michael applied or how cold he made them, they wouldn't turn into liquids. Because of this, he called them permanent gases, thinking they might never be liquefied. But science kept moving forward. In the 1860s, an Irish scientist named Thomas Andrews took on the challenge. He studied the behavior of gases more deeply. Andrews discovered something called the critical temperature. This is a specific temperature for each gas, below which the gas can be turned into a liquid if enough pressure is applied. Above this temperature, no amount of pressure will make the gas liquefy. Andrews found that every gas has its own critical temperature and pressure. This discovery was crucial because it explained why some gases couldn't be liquefied at the temperatures and pressures that Michael had used. With this new understanding, scientists could find ways to liquefy even the so-called permanent gases by achieving lower temperatures. Understanding how matter behaves at different temperatures and pressures was essential for advancing science. Andrews' work paved the way for other scientists to explore the properties of materials at extremely low temperatures, which eventually led to the discovery of superconductivity. In 1877, a French scientist named Louis-Paul Cailletet achieved something remarkable. He turned oxygen gas into a liquid for the first time. He did this by squeezing the oxygen gas very tightly in a strong steel container, using pressures over 300 times that of normal air pressure. Then, he suddenly released the pressure, causing the gas to cool down rapidly and condense into liquid oxygen. Before this achievement, scientists knew that gases could turn into liquids at low enough temperatures, but gases like oxygen, nitrogen, and hydrogen were called permanent gases, because no one had been able to liquefy them. One big challenge was reaching the extremely low temperatures needed to turn these gases into liquids. Cailletet's success came from his clever use of quickly releasing pressure to cool the gas. Around the same time, a Swiss scientist named Raoul Pictet also managed to liquefy oxygen, but he used a different method involving a series of cooling steps with other cold liquids. The successes of Caillet and Pictet marked the first times that oxygen had been turned into a liquid by human efforts. By the mid-1870s, most known gases had been turned into liquids because of advances in cooling technology and a better understanding of how gases behave under different pressures and temperatures. However, hydrogen remained a problem. With a boiling point of about -253 degrees Celsius, hydrogen was much harder to liquefy than other gases, posing a big challenge for scientists at the time. The equipment and methods available in the 19th century just weren't enough to reach such low temperatures. Scientists like James Dewar were determined to solve this problem. Dewar was a Scottish chemist and physicist who invented a special kind of flask that could keep things very cold by reducing heat transfer. In 1898, after many failed attempts, Dewar finally succeeded in turning hydrogen gas into a liquid using advanced cooling techniques. After oxygen and air had been liquefied by other scientists, Dewar overcame significant experimental challenges to condense hydrogen by lowering the temperature to -259 degrees Celsius. At such low temperatures, almost all known gases easily turned into liquids, except for helium, which had been discovered in the atmosphere in 1895. Attempts by scientists like Olszewski, Dewar, and Travers to liquefy helium didn't work, and many people thought it might be impossible. By the early 20th century, one of the most important figures in the history of superconductivity emerged, Heike Kamerlingh Onnes, who discovered the superconducting phenomenon. Onnes was a Dutch physicist born in 1853 who was particularly interested in how materials behaved at very low temperatures. He believed that by cooling materials down to extremely low temperatures, we could learn about their fundamental properties. His laboratory at the University of Leiden in the Netherlands became a leading center for research in low-temperature physics. For years, Onnes worked to improve the cooling techniques developed by other scientists. In 1906, he discovered a way to produce large amounts of liquid hydrogen by building an advanced machine for liquefying hydrogen. In 1908, this achievement allowed him to reach one of his main long-term goals, turning helium gas into a liquid. He found out that liquid helium's temperature was about -269 degrees Celsius, just a few degrees above absolute zero, which is -273.15 degrees Celsius. On July 10, 1908, after years of hard work and technical innovation, Onnes successfully liquefied helium. To do this, he built advanced vacuum pumps and cooling systems to gradually lower the temperature. The key was using a series of cooling steps, each one lowering the temperature further by using the cooling effects of gas expansion and evaporation. By isolating helium and cooling it to -269 degrees Celsius, he finally made a breakthrough. This event marked the first time helium had ever been turned into a liquid by human technology, creating the lowest temperature achieved at the time and pushing science closer to absolute zero. The achievement of liquefying helium in 1908 was a major milestone in the history of low-temperature physics. This breakthrough had profound effects on the study of matter at extremely low temperatures and laid the foundation for fields such as superconductivity and quantum physics. At the time, it was known that the resistance of metals, their opposition to the flow of electric current, decreased as the temperature was lowered. However, it was unclear whether this trend would continue all the way down to absolute zero. Some scientists, including Lord Kelvin, thought that resistance might increase again as the temperature approached absolute zero, possibly due to some unknown effect. In 1911, Onnes conducted an experiment using liquid helium, which he had successfully liquefied in 1908, to cool mercury to temperatures near absolute zero. His goal was to carefully measure how mercury's resistance changed at extremely low temperatures. To Onnes's amazement, when he cooled mercury to minus 269 degrees Celsius, its resistance suddenly disappeared. Mercury had entered a new state, showing zero resistance, a property he called superconductivity. This meant that electric current could flow through mercury without losing any energy. It was a revolutionary discovery because resistance usually causes energy loss in the form of heat. In recognition of his groundbreaking work on superconductivity, Heike Kamerlingh Onnes was awarded the Nobel Prize in Physics in 1913. His experiments not only advanced the field of low-temperature physics, but also opened new doors in understanding quantum phenomena and how materials behave at extremely low temperatures. In 1933, German physicists Walther Meissner and Robert Oxenfeld made another significant discovery while studying superconducting materials. They observed that when certain materials transition into the superconducting state below a critical temperature, they expel all magnetic fields from their interior, a phenomenon now known as the Meissner effect. This was a pivotal finding because it showed that superconductivity is not just about zero electrical resistance. It also involves perfect diamagnetism. The Meissner effect demonstrated that superconductors could repel magnetic fields entirely, leading to effects like magnetic levitation. The discovery of the Meissner effect was crucial as it indicated that superconductivity represents a distinct thermodynamic phase, characterized by both zero electrical resistance and the expulsion of magnetic fields. This phenomenon couldn't be explained by existing theories at the time, which treated superconductivity merely as an extreme case of conductivity. The Meissner effect challenged scientists to develop new theoretical frameworks to fully understand superconductivity. After the discoveries of superconductivity and the Meissner effect, scientists began working on theories to explain this astonishing phenomenon. This process took decades of exploration and repeated testing. Researchers wanted to understand why certain materials would suddenly lose resistance at extremely low temperatures, and tried to predict which other materials might show similar properties. These early theoretical explorations laid the groundwork for later, more complete theories of superconductivity and inspired scientists to search for new types of superconductors. A significant theory, known as the BCS theory, explained the superconducting phenomenon in traditional superconductors. It suggested that electrons could pair up in a way that allowed them to move through the material without resistance. However, at that time, achieving superconductivity at higher, more practical temperatures seemed impossible. In practical applications, superconductors are highly valuable in fields like magnetic levitation, such as in maglev trains. Superconducting materials can repel strong magnets, allowing for frictionless movement. In the 1950s, scientists had noticed strange behaviors in certain materials when they were cooled down to extremely low temperatures. These materials seemed to conduct electricity without any resistance, meaning they could carry electric current without losing energy. They also expelled magnetic fields in a phenomenon called the Meissner effect. However, nobody understood why these things happened or how electrons, the tiny particles that carry electricity, could move so smoothly in these conditions. Around this time, a physicist named John Bardeen, already famous for co-inventing the transistor, became interested in these mysteries of superconductivity. He started working with two other scientists, Leon Cooper and Robert Schrieffer, to try to figure it out. Together, they would eventually develop a groundbreaking explanation for superconductivity, now called the BCS theory, named after their initials. In 1956, Leon Cooper made a critical discovery. Electrons, which normally repel each other, could sometimes form pairs if the conditions were just right, especially at very low temperatures. Cooper showed that these paired electrons, now known as Cooper pairs, could actually behave in a way that overcame their natural repulsion. Usually, individual electrons follow a strict rule that keeps them from occupying the same space, but when they form Cooper pairs, they act differently. Together, they behave more like a group, allowing many pairs to share the same space and energy, a key ingredient for superconductivity. Cooper realized that this pairing happened because of an interaction between electrons and the tiny vibrations in the material's structure. When one electron moves through the material, it slightly shifts the atoms around it, creating a small positive area that attracts another electron, forming a Cooper pair. Since this paired state has lower energy than if the electrons were separate, it's more stable, especially at low temperatures. Once these Cooper pairs form, they start moving together in a synchronized way through the material. Unlike single electrons, which usually get bounced around by impurities or tiny vibrations in the material, Cooper pairs glide smoothly, encountering no resistance. This smooth movement of Cooper pairs is what allows superconductors to carry current without losing energy. Guided by Bardeen and Cooper's ideas, Robert Schrieffer developed the math to describe this behavior. He came up with equations that showed how all these Cooper pairs could act as one group, moving without resistance and creating the unique properties of superconductors. In 1957, Bardeen, Cooper, and Schrieffer published their theory, which immediately changed how scientists understood superconductivity. One of the key ideas in their theory was the concept of an energy gap. This gap acts like a shield that prevents small disturbances from breaking the Cooper pairs, keeping the superconducting state stable. However, if the material gets too warm, this energy gap can't protect the Cooper pairs, and the material loses its superconducting properties, returning to its normal state. This explains why superconductors need to be kept very cold to work. The BCS theory not only solved long-standing mysteries, but also quickly found support from experimental results, helping scientists understand important details like the temperature at which superconductors lose their resistance. This theory didn't just explain low-temperature superconductors, but also influenced research in many other fields of physics. The impact of BCS theory has been huge. It led to the development of superconducting magnets used in MRI machines and particle accelerators. It has also inspired studies in other areas like quantum computing and superfluidity. Although BCS theory couldn't explain the newer high-temperature superconductors found in the 1980s, it remains a foundation of physics research. For their work, Bardeen, Cooper, and Schrieffer received the Nobel Prize in Physics in 1972, recognizing their achievement in explaining superconductivity. Remarkably, this was Bardeen's second Nobel Prize in Physics, an honor that reflects his incredible contributions to science. The discoveries made by Bardeen, Cooper, and Schrieffer continue to drive new advances in physics and technology, showing the lasting impact of their groundbreaking theory. Despite these advancements, the quest to achieve superconductivity at higher temperatures persisted, pushing scientists to explore beyond the boundaries of existing theories. In the early days of superconductivity research, scientists focused their efforts on studying pure elements like mercury, lead, and tin. This focus made sense because back then, simpler materials were easier to handle. These elements have straightforward atomic structures, unlike more complex materials with mixed atoms, which were hard to study with the limited scientific tools and theories of the time. Superconductivity was still a mysterious phenomenon, and scientists didn't know exactly how or why it worked. In fact, it wasn't until 1957 that a group of scientists, John Bardeen, Leon Cooper, and Robert Schrieffer, created a theory that explained superconductivity. Known as the BCS theory, this explanation helped researchers finally understand what was happening at the atomic level when materials became superconductive. However, the theory also suggested that achieving superconductivity at much higher temperatures would be almost impossible, due to the limitations of how electrons interacted in these materials. For many years, scientists believed that superconductivity could only happen at extremely low temperatures, typically below minus 269 degrees Celsius. To reach such low temperatures, they had to use liquid helium, which is expensive and challenging to handle. Because of these limitations, superconductors weren't very practical outside of scientific research. As technology advanced and experimental techniques improved, scientists began to revisit and test more complex materials, hoping to find exceptions to the limitations suggested by the BCS theory. Eventually, they began testing more complex materials like alloys and compounds. These materials brought some unexpected surprises. Researchers found that certain alloys could reach higher superconductive temperatures than pure elements, sparking interest in a new range of materials. the scientific community started exploring compounds, setting the stage for a groundbreaking discovery. In 1986, a major shift happened. Two physicists, Carl Alexander Miller and Johannes Georg Bednorz, working in a lab in Zurich, Switzerland, became interested in ceramics, a group of materials that usually don't conduct electricity well. However, Miller and Bednorz saw potential in ceramic materials made from metal oxides, especially a family called perovskites, known for their unique crystal structure. Through careful and patient experimentation, Miller and Bednorz made a thrilling discovery. They found that a ceramic material called lanthanum barium copper oxide could become superconductive at around -238.115 degrees Celsius, which was a much higher temperature than any previous findings. This was a breakthrough moment, even though -238.15 degrees Celsius still required cooling with liquid helium. Their findings were initially met with skepticism, so they published their results cautiously, choosing a small scientific journal and using careful wording. However, their work was soon confirmed by labs around the world, leading scientists to realize that high-temperature superconductivity was indeed possible. This sparked a rush to explore other materials in hopes of pushing the temperature limits even further. In the midst of this global effort, just a few months later, another breakthrough came in early 1987. A team led by Chu-Ching Wu at the University of Houston discovered a new material, yttrium barium copper oxide, YBCO, which could reach superconductivity at an even higher temperature, -181.15 degrees Celsius. This was a game changer because -181.115 degrees Celsius is above the boiling point of liquid nitrogen, which is much more affordable and practical than liquid helium. For the first time, scientists could cool superconductors using liquid nitrogen, making the technology far more accessible. This new material, YBCO, allowed superconductivity to be achieved under much more practical conditions, opening up possibilities for applications like efficient power systems, faster electronics, and magnetic levitation technology, which powers maglev trains. Although challenges remained in making these materials widely available, this discovery was a turning point in science and technology. Recognizing the monumental impact of these developments, the scientific community celebrated the pioneers of this new era. The impact of Miller and Bednorz's discovery was so immediate and transformative that they were awarded the Nobel Prize in Physics in 1987, just over a year after their groundbreaking work. This was one of the fastest recognitions in Nobel history, underscoring the importance of their contribution. Their work launched a new era in superconductivity research, with scientists around the world racing to find materials that could operate at even higher temperatures. Within a few years, researchers discovered other copper oxide-based materials that could reach up to -148.15 degrees Celsius, pushing the boundaries of what was possible and making the dream of practical superconductors closer than ever. These advancements didn't just expand scientific knowledge, they opened doors to practical applications that could revolutionize technology. One of the most fascinating uses of superconductivity is in particle accelerators. Imagine a machine so powerful it can take tiny particles, like protons, and hurl them around at nearly the speed of light. This machine, called a particle accelerator, helps scientists explore mysteries about the universe's very beginnings. The Large Hadron Collider, LHC, located underground near Geneva, Switzerland, is one of the largest and most advanced of these machines. By smashing particles together at extraordinary speeds, the LHC creates conditions similar to those right after the Big Bang, allowing scientists to study the building blocks of everything around us. To make all of this possible, the LHC relies on special devices called superconducting magnets. These magnets create super strong magnetic fields, which guide the particles as they speed through a long circular tunnel that stretches for 27 kilometers beneath the French-Swiss border. Without these magnets, the particles would fly straight off course, missing their mark entirely. The magnets serve a few crucial roles. First, they bend the path of particles, keeping them on a loop instead of letting them fly off in a straight line. Second, they focus the particle beams, keeping them tightly packed together. This focus makes collisions more likely, which is essential for capturing the tiny particles and energy bursts that result from these crashes. What makes these magnets so effective is that they're made from special materials, which, when supercooled to almost the lowest possible temperature, lose all electrical resistance. This allows them to carry huge amounts of electric current without wasting energy, creating the powerful magnetic fields needed to control the particles. The LHC's superconducting magnets are made from materials like niobium titanium. These materials become superconducting at temperatures close to absolute zero. To reach such extreme temperatures, the LHC's magnets are chilled with liquid helium, dropping to about -271.3 degrees Celsius. At these temperatures, they can handle very high currents, producing a magnetic force strong enough to keep the particles on track as they travel close to the speed of light. Without superconductors, building a machine like the LHC would be nearly impossible. The amount of energy needed to control particles moving that fast would be too enormous, making the accelerator too large and expensive to run. The unique properties of superconductors make them indispensable for such advanced technology. Thanks to superconductors, scientists can carry out these high-energy experiments in a realistic way, using manageable amounts of power. The LHC has already led to some groundbreaking discoveries made possible by these superconducting magnets. One of the most famous is the Higgs boson, sometimes called the God particle. This particle was first predicted in the 1960s and plays a key role in explaining why some particles have mass. After years of searching, scientists at the LHC finally found evidence of it in 2012, confirming an important part of modern physics theories. The discovery of the Higgs boson was huge, as it validated the standard model of particle physics, a theory that describes how fundamental particles and forces interact. By uncovering the Higgs boson, scientists gained critical data that not only strengthens existing theories, but also opens new paths for understanding dark matter and other cosmic mysteries. The LHC's findings highlight how essential these large research facilities are in advancing human knowledge and how international collaboration can push the boundaries of what we know about the universe. Superconducting magnets are the unsung heroes that make the LHC and other particle accelerators possible. They allow particles to reach extreme speeds and energies, creating a window into the universe's smallest components and its deepest secrets. But the impact of superconducting magnets isn't limited to particle physics. They also have significant applications in the medical field. One such critical application is in MRI machines. Superconducting magnets are crucial in MRI machines, providing non-invasive medical imaging essential for modern diagnostics. MRI machines rely on powerful magnetic fields to produce detailed images of organs, tissues, and other internal structures. These fields need to be extremely strong and stable for the MRI to work effectively. That's where superconducting magnets come into play. Superconductors are materials that, when cooled to extremely low temperatures, near absolute zero, completely lose electrical resistance. This allows them to conduct current without any energy loss or heat generation due to electrical resistance, making it possible to maintain a strong, stable magnetic field without needing a continuous electrical power supply. However, they do require continuous cooling to stay superconducting, typically using liquid helium. During an MRI scan, the superconducting magnet creates a magnetic field that aligns the hydrogen atoms in the body. When a radiofrequency pulse is applied, these atoms are knocked out of alignment, and as they return to their original state, they emit signals. These signals are captured by the MRI machine and used to construct detailed images of the body. Superconducting magnets are essential because the strength and uniformity of the magnetic field directly impact image quality. Resistive electromagnets would consume vast amounts of power and generate excessive heat due to electrical resistance, making it impractical to achieve the high-resolution images needed for accurate diagnostics. Plus, maintaining a stable magnetic field is crucial to avoiding image distortion or noise, which could affect diagnostic accuracy. By utilizing superconducting magnets, MRI, or magnetic resonance imaging has several advantages over other imaging methods. Here are a few key benefits. First, it's non-invasive. Unlike X-rays or CT scans, MRI doesn't involve ionizing radiation, making it a safer option for imaging. This is particularly important when scanning sensitive areas like the brain or spinal cord multiple times, where safety is a top priority. Second, MRI machines offer exceptionally high-quality images. MRI provides incredibly detailed images of soft tissues, making it invaluable for diagnosing tumors, nerve damage, or detecting abnormalities in organs like the liver, brain, or heart. It captures internal details with greater accuracy, giving doctors clearer insights for diagnosis. This precision helps in early detection of diseases, which can be crucial for successful treatment outcomes. Third, there's the aspect of efficiency. Thanks to superconducting magnets, MRI scans are more efficient and can be more cost-effective in terms of electrical energy consumption. Once the magnet is activated and brought to a superconducting state, it doesn't require a constant electrical power supply to maintain the magnetic field, which reduces operating costs related to electricity. However, there are costs associated with maintaining the cooling systems necessary for superconductivity. These cooling systems are essential to keep the magnets at the low temperatures required for superconductivity, but they can be expensive to operate. One of the main challenges of using superconducting magnets is the need for cooling, typically using liquid helium to maintain superconducting temperatures. However, advancements in magnet technology, like the development of high-temperature superconductors, aim to reduce the complexity and cost of cooling systems. As of now, these technologies are still being developed and are not yet standard in commercial MRI machines. Future innovations in this area hold the promise of making MRI technology even more accessible and efficient. In conclusion, superconducting magnets are at the heart of MRI technology. They create the powerful and stable magnetic fields that produce high-quality, non-invasive images, making MRI a cornerstone of modern medical diagnostics. Shifting from medical imaging to transportation, the influence of superconducting magnets extends even further. Imagine a world where you can glide from one city to another at astonishing speeds of over 300 miles per hour, without feeling a single jolt or hearing the rhythmic noise of wheels clattering on tracks. This isn't a distant dream. It's the near-future promise of maglev trains, an innovative technology that uses magnetic levitation to provide a frictionless, smooth travel experience, potentially redefining how we think about transportation. At the heart of maglev, or magnetic levitation, lies a principle that defies traditional rail mechanics. Instead of relying on wheels that roll along tracks, maglev trains float above them, lifted by powerful magnetic forces. This suspension eliminates the main culprit of slowing down traditional trains, friction. When friction is nearly eliminated, as it is with maglev technology, travel becomes more efficient and speeds increase dramatically. It's this frictionless advantage that enables maglev trains to achieve previously unimaginable velocities, all while offering a level of comfort and quietness for passengers that conventional trains can't match. The technology behind maglev trains is based on two main types of magnetic levitation systems, each with its unique mechanics. The first, known as electromagnetic suspension, EMS, is somewhat like a fridge magnet, but on a much larger scale and far more dynamic. In EMS systems, standard electromagnets on the train attract it to magnetic rails on the track, allowing it to hover just above them. Germany's Transrapid system, a prime example of EMS, uses precisely controlled magnetic forces to keep the train stable and levitating, with sensors that continually adjust to keep the train centered and hovering at just the right height. A second, more sophisticated method is electrodynamic suspension, EDS, which relies on advanced magnets, often superconducting ones, that create powerful repulsive forces with the track. As the train moves, the magnets induce electric currents in coils within the track, generating magnetic fields that repel the train upwards. This effect is similar to trying to push two like poles of magnets together. They refuse to touch. Japan's SC maglev train, which uses this technique, has set speed records using EDS to float above the tracks with near-zero friction, providing a glimpse into the future of ultra-fast, smooth travel. Superconductors, materials that lose all electrical resistance at extremely low temperatures, play a vital role in the EDS system. These materials are capable of producing magnetic fields stronger than anything conventional magnets can achieve, which enhances both the train's levitation and stability. However, using superconductors isn't without challenges. Keeping them at these low temperatures requires a significant amount of energy, as well as specialized cooling systems. While superconductors add efficiency by reducing electrical resistance, they also come with higher energy costs and operational complexities, making their widespread adoption a gradual process. For a maglev train, levitation is just part of the journey. The next challenge is propulsion. Maglev trains use a series of linear motors along the track to generate a moving magnetic field. This magnetic field interacts with the magnets on the train, creating a forward thrust that propels it smoothly and at high speed. This propulsion system, combined with continuous, precise adjustments to the magnetic forces keeping the train levitated, makes for an incredibly stable, quiet, and swift ride, much like balancing a ball on a jet of air, where subtle shifts in pressure keep everything centered. In practical terms, maglev trains bring numerous advantages over traditional rail systems. Their lack of physical contact with the track means fewer moving parts, significantly reducing the wear and tear seen in conventional trains. This reduces maintenance costs and improves overall system durability. For passengers, the absence of wheel-on-rail friction results in a quieter and smoother journey, while maglev trains' streamlined design allows for a faster, more efficient experience. Environmentally, they also offer benefits, reducing both noise pollution and emissions compared to traditional train systems, positioning maglev as a greener travel option. Moreover, the increased efficiency leads to shorter travel times, making maglev trains a competitive alternative to air travel over certain distances. Yet, despite these advantages, there are obstacles to overcome. Building the necessary infrastructure for maglev trains is costly, especially when factoring in the expense of superconductors and the cooling systems required to maintain their low temperatures. Additionally, the requirement for entirely new tracks that are incompatible with existing rail networks adds to the complexity and expense. High energy consumption for these systems is another hurdle, as is the newness of the technology, which has led to only a few operational lines worldwide, such as the Shanghai maglev. For maglev trains to become commonplace, the technology will need to become more affordable and accessible. Looking to the future, advancements in high-temperature superconductors could be the breakthrough that maglev technology needs. These materials would reduce the need for intensive cooling, making the system less energy-dependent and more practical. This would not only lower operational costs, but also make the technology more environmentally friendly by decreasing energy consumption. If such developments continue, we may see maglev trains connecting cities across continents, offering an unparalleled travel experience. Ultimately, maglev trains are more than just a novel idea. They're a pioneering step toward a future where we can travel faster, smoother, and more sustainably. They blend advanced physics with a simple vision to overcome the constraints of friction and traditional rail mechanics, transforming travel into a high-speed, floating journey. As research progresses, this vision becomes increasingly attainable, promising significant changes in how we approach transportation. So next time you're caught in a traffic jam or waiting for a delayed flight, picture a world where, instead, you could step onto a train that glides effortlessly to your destination, floating above the track at remarkable speeds. Recently, there's been big news in the world of superconductivity. A Korean research team claims to have discovered a room-temperature superconductor called LK99. This discovery has grabbed a lot of attention and sparked discussions in the scientific community because, if room-temperature superconductivity can be achieved, it could revolutionize areas like energy transmission and electronic devices. Such a breakthrough would eliminate the need for costly cooling systems, making superconducting technology more practical and widespread. However, the superconducting properties of LK99 are still controversial and need verification from more independent laboratories. Unfortunately, up to now, other independent labs haven't successfully replicated or confirmed the room temperature superconducting properties of LK99. This has led to skepticism and debates within the scientific community about these claims. Replication is a cornerstone of the scientific method, and until consistent results are achieved, the claim remains unproven. Nevertheless, this event highlights once again the importance and challenges of researching room temperature superconductivity, and it has reignited ongoing interest and exploration in this field. Exploring the phenomenon of superconductivity has always been one of the most influential and challenging pursuits in physics. From early low-temperature research, the discovery of superconductivity, the development of its theoretical foundations, and the breakthrough of high-temperature superconductors, We're now pushing the boundaries towards room temperature superconductivity. This field's progress hasn't just advanced physics. It's opened doors to new technological possibilities for the future. Think of everything from maglev trains to more efficient power transmission. The potential applications for superconductivity are vast. Yet, despite the impressive progress, achieving room temperature superconductors remains a major challenge, continuing to captivate scientists worldwide. Each step forward brings us closer to a future where the limitations of current technology are overcome, potentially transforming industries and daily life.